Alright, so odd ones out. In this problem, we're being asked to draw a DFA that decides the language L, where L is the set of all strings that have an even number of ones and an odd number of zeros. And of course, we need to give you an alphabet, which is just going to be 0 and 1. So before we actually begin making this DFA, I want to make sure that we all have kind of a shared understanding of what exactly this language is. So of course, there's two different parts of the language. We have an even number of ones, and then every string also needs an odd number of zeros. And we can go through a few examples too. So empty string is not going to be in our language because our empty string has 0 ones and 0 zeros, and 0 is not odd. Now if we just look at a single zero has 1 0 in it, which is going to be odd. So that will be in the language. And then we have a few more normal examples. So 1 1 0, we have 2 ones, 1 0, and so on and so forth. Just whenever you have an even number of ones and an odd number of zeros, it's going to be in your language. So now let's actually try to start tackling the problem of making this DFA. And the way I'm going to do this is I'm just going to look at half of this problem here, which is just going to be trying to decide if a string has an even number of ones. And actually in lecture, we did see a DFA that would do this, that looks a little something like that. And if we want to actually convince ourselves that this might be true, we can run through an example, which is over here. So we have 4 ones in this example, so I'd hope that this DFA accepts this. So we start off at Q0, we read 3 ones, which is going to bring us to Q1, Q0 and back to Q1. We read 2 zeros, which is going to keep us in Q1 over here. We read 1 1, which is going to bring us to Q0, and then we read our final character, which is just a 0, and that's going to keep us in Q0. And now that our string's over, we can look at if we're in an accepting state. Q0 is an accepting state, so we're going to go ahead and accept. And that's exactly what we should be doing. So hopefully this makes some intuitive sense as to how it's deciding if a string has an even number of ones. And it might help some more to actually look at exactly what each of these states are doing over here. So if we look at Q0, we can see that Q0 represents whenever your string has an even number of ones, and then Q1 is going to represent when a string has an odd number of ones. And whenever we read a 1, you'll see that we have these lines kind of bouncing back and forth between Q0 and Q1, and that lets us transition from an even number of ones to an odd number of ones and back and forth when we keep reading ones, and the evenness and oddness changes. And then for the other part of the problem, which is odd number of zeros, I claim that this is basically almost exactly the same DFA. All you need to do really is just switch the ones with zeros and then switch the accepting state from Q0 to Q1 because you want to accept odd things instead of even things. And then the structure is basically exactly the same. So hopefully now that we have kind of an understanding of how we can decide half of this language, we can start to tackle the actual language, which is combining an even number of ones and an odd number of zeros. And I think some of you in your head, you might already have this picture of what this DFA should look like. But I want to take a little bit of more of a systematic approach, just so you can have kind of a picture in your mind of how you should approach DFA problems when they start to get a little bit more difficult. And to do that, I have this motivating question, which is, what exactly do we need to keep track of? And the reason I'm asking this question is if we can figure out maybe how many things we need to keep track of, then we can relate these to the number of states that we use. And if you remember, kind of the fundamental limitation of a DFA is that you have a finite number of states, and you can only remember exactly the things that you encoded in these states. So if you have like 5 states, you can only remember 5 different things. So if we figure out first how many things we need to keep track of, we can try to relate each of these things to a state and then kind of massage our way to a DFA from there. So I think that this language is pretty clear that we need to keep track of both an even and odd number of ones, and then also the even and oddness of zeros. And we need to keep track of both of these, so I can make this little table over here and kind of just fill out these 4 rows, since we have even and odd for both ones and zeros. And then, so you'll see we have 4 different things over here, and we can try to maybe, as I was saying earlier, relate these to 4 different things that we need to keep track of to 4 different states. So we have Q0 through Q3. And then, now that we're kind of working on this, we can try to then figure out, what we want to start with, and then maybe which states we would accept. So when we start, we have an empty string, that's going to give us even and even, so we probably want to start at this state Q0. And then we only want to accept strings that have an even number of ones and an odd number of zeros, and that's literally just written right here. We have even ones, odd zeros, that's exactly what we want to accept, state Q2, which is highlighted right here. So then I can go ahead and I can put our 4 states on our slide over here. And now that we have the states, we have our starting state, we have our accepting states, and we also have our alphabet, there's only one more thing that we need to figure out in order to get this into a DFA, which is going to be our transition function. So at this point, I would advise you to take a minute, try to see if you can come up with a transition function that would work for this. And if you can come up with this transition function, then maybe you can try to start drawing the lines over here and seeing what exactly this DFA would look like. But if we look at our intuition from before, which is our DFA that decided an even number of ones, we can kind of take similar concepts over here. And I'm actually going to kind of basically just copy exactly what they did, which is whenever we read a 1, we want to switch the parity or the even and oddness of the ones place in our state. So for example, if we're at Q0 and we have an even number of ones and an even number of zeros, and then we read a 1, then our 1s switch to odd. So we're going to switch over to Q1, which is the same as Q0, just with a flipped 1 state. And then since we need to keep track of both 1s and zeros, maybe we should do the same thing for zeros too. So for example, if you're at Q0 and you read a 0, you want to switch your zeros to odd. So you're going to go from Q0 to Q2. So this is actually all we need for a transition function. Of course, it's not very rigorous. You can do that on your own. But since the only thing we can possibly read are zeros and ones, now that we've said what we want to do for both zeros and ones, that's all we need for our transition function. So take a minute and try to convince yourself that these 2 rules will actually be able to keep track of what the even and oddness is of both zeros and ones. So now that we've had this transition function, let's actually go ahead and draw these arrows on our DFA over here. So starting with when a 1 is read, let's take a look at state Q0, and you might see that we want to switch between Q0 and Q1 depending on when our 1 is read. So we can add these 2 arrows over here. And then the same thing for Q2. Whenever we're in Q2 and we read a 1, we want to switch to Q3 and then back to Q2 over and over, and that gives us our next 2 arrows. And then we pretty much just want to do the same thing for 0, except it's going to be the other direction over here. So this is actually going to be our full DFA. So we have all of our lines that we need, we have all of the transitions, we have our starting state, and we have our finishing state. And you'll see that this might be useful for some intuition later, but you'll start to see that we have these 1 lines on our rows, so between Q0 and Q1, and then 2 and 3, and then the 0 lines are in our columns over here. And let's see what happens when we run this through a few examples. So 1 0 1 0 has an even number of 1s and an even number of zeros, so we would expect to reject. So we start at Q0, we read a 1, we read a 0, we read another 1, and then we read our final 0, and that brings us back to Q0, and Q0 is not an accepting state, so we're going to reject correctly. And then again, if we have our longer example, we have 4 1s and 3 zeros, which is going to be, we're expecting this to accept. So let's do 1 1 1, 0 0, 1, and then finally 0 brings us back down to Q2, and that's going to be an accepting state, so we're going to accept correctly. And this is actually exactly the solution to this problem over here. And if you want to, you can go ahead, take this a little bit further, try to formalize it and actually write out the 5 tuple of the DFA that we have over here. So now that we've finished doing our problem, I just want to go over a few different takeaways. So the first 2 are just some generic steps that maybe you should take if you're trying to approach a new problem about constructing a DFA from a language. And basically, just do something similar to what we did here, which is trying to figure out exactly what you need to keep track of in your DFA. And when you figure this out, you can try to convert these into actual DFA states that you can connect to each other. And then beyond this, I just want to give a bit more intuition about the proof that's in the textbook about the intersection or also the union of 2 different languages. And we can do this here because this language that we're deciding here is actually in fact an intersection of L1 and L2, which are all binary strings with the even number of 1s and all binary strings to the odd number of zeros. And we know from the textbook that the intersection of these 2 languages are also going to be regular. So in the textbook, when we're trying to prove that the intersection of 2 regular languages are regular, we use something called a Cartesian product, which is basically just taking all the states in L1 and then producting them together or multiplying them together with all the states of L2. And we're combining these states together. And we can see this visually over here, actually, because if we look at this DFA, the same structure can be used to decide both L1 or L2 with just some moving around of the zeros and ones. And you can actually see this product going on visually in our DFA that we just made, because if we look at L1, we can see that we're deciding it along the rows or along the x-axis. So we have these 1 arrows, and then with L2, we're deciding this along the y-axis, which is going to be our 0 arrows going up and down. And then in a Cartesian product, a lot of the times you might represent it by having one thing on the x-axis and then you're just combining it with something on the y-axis. It's basically what we're doing here too, because we have our 1 or L1 deciding network, or L1 deciding DFA on the x-axis, and our L2 deciding DFA on the y-axis. And then we just combine these states together into kind of hybrid states where we represent both the evenness and the oddness of ones and zeros in all 4 of these states here. So hopefully that gives you some more intuition about how the intersection of regular languages are regular, or also the union of regular languages are regular.